there are several more applications of relative motion. We will look at some of these applications. The first one is the minimum distance problems. Minimum distance problems. Now I will show you by an example. So the problem is like this: there are two crossroads. There are these two crossroads, and this is a junction. And while at a certain time, there are two cars. Now this is car A, and this one is car B. At a certain moment, car A is having velocity of suppose 3 kilometer per hour, and car B is having a velocity of 4 kilometer per hour, and at this moment the distance is 20 kilometer, like this. So let us write the statement of the problem, that cars A and B are traveling with velocities 3 kilometer per hour and 4 kilometer per hour respectively, as shown in the diagram, as shown in figure. This is at a certain moment. So during their journey, during their motion, find minimum distance between A and B. Okay, so to find minimum distance, so you can so as a function of time you can find distance and then apply maxima and minima, but we are not going to do that. That you can try out, but we are going to use the method of relative motion. Now what we'll do, we will observe from any one of the cars. So let's make it car B. So let's make car B as the reference frame. Reference frame means you observe all the situations from car B. So with respect to car B, car A is at rest. Now this is car A. Velocity of A with respect to B will be velocity of A minus velocity of B. Now this is velocity of A vector, and velocity of B is there, so minus of velocity of B is this way, minus VB, while the magnitudes will remain same even if it is subtracted. So this happens to be 3 kilometer per hour, and this happens to be 4 kilometer per hour, and so the resultant velocity, resultant of VA and minus VB is velocity of A as seen by B. So this is so with respect to B, so A will travel in such a path and with a velocity of how much? So what is the magnitude of VA with respect to B? So it's root over 3 square plus 4 square, that is 5 kilometer per hour. And more importantly, as you can see from the diagram, this is 3, this is 4, so this will be 37 degree. This angle is 37 degree. Tan 37 is 3 by 4, and the minimum distance, as observed, the minimum distance between the cars A and B. See here I have fixed B. B is a reference. So with respect to B, this is the path taken by A. So minimum distance is obviously when car A is here. So it's a perpendicular distance. So let's find that out. So D minimum. So minimum distance between A and B, this D minimum will be equal to how much? This is 20. This distance is 20 kilometer. So it's 20 kilometer. So this is So 20 sine 37, right? 20 sine 37 kilometer, that is sine 37 is 3 by 5, so that 12 kilometer. Minimum distance between A and B is 20 kilometer. And say if it is asked that, okay, so from this starting position when B and A were here as shown in the diagram, B was here and A was here, from this position, I mean, if you take this as time t equal to 0, find the time after which the distance between A and B is minimum. Now, that's also very easy to find out. That, see this, so if it asks that what time after what time distance between A and B is minimum, I mean that time, the count of the time starts from this position, this time 0. So as seen by B, so A will cover a distance how much? This is 20 cos 37, so that's 20 cos 37 distance divided by velocity. Now this velocity will be relative velocity, that is VA with respect to B, so that happens to be 20 cos 37 means 4 by 5 divided by VA with respect to B is 5, this much hour, so it happens to be how much? 16 by 5 hour. By alternate method you can solve it by calculus, so I'll just show you briefly how it's done by maxima and minima. Now this is the time t equal to 0 and we'll work in this kilometer per hour itself. So after certain time t, A is here, so it goes how much distance? A goes 3t kilometer, right? This is kilometer, and this B is here, so B goes a distance 40 kilometer. Okay, so this happens to be how much? 20 minus 40 kilometer. So this is the distance between A and B. So let's write this S. S is distance between A and B in time, or in after time t. After time 0 starts from here, A here and B here. So this S happens to be equal to root over of 3t square plus 20 minus 4t square, so that you can simplify this S. So ds dt, so when S is minimum, you have to substitute this ds by dt is equal to 0. ds by dt is equal to 0. Let's see. So here so ds by dt is actually this. Now this that's 90 square, right? So 18 t plus this is 2 into 20 minus 40 multiplied by minus 40, so that's equal to 0 for S to be minimum. So here see, so the numerator is equal to 0, so there you get 90 minus this to be go of 4 into 20 minus 40 is equal to 0. So what you get here? 90 minus 80 plus 40 equal to 0. No, sorry, that's 16, right? 16. So how much is that? 9 plus 16, 25t equal to 80. So t is equal to 80 by 25. 80 by 25, I guess it's 16 by 5 hour. So here see, we have got also the same answer by this method, relative velocity method. If you have to calculate the time after which the distance between A and B is minimum. So by this approach of calculus, maxima and minima, in this case we get t equal to 16 by 5 hour. Now this t 16 by 5 hour, this value of t as calculated here has to be substituted back into this equation. If you substitute this t 16 by 5 hour, you will get that value we have got calculated before, that is 12 kilometer. So this is the minimum distance problem. Okay, now you have one more important thing, that is relative motion between projectiles. Relative motion between projectiles may seem to be very difficult, because both the projectiles are flying in air, and while they are flying, what is the relative motion between them? Now see, say this projectile A and this is projectile B while they are flying. So as seen by say B, the motion of A is obviously a straight line. I will explain it why it's a straight line. A straight line with constant velocity. Obviously constant velocity means it is straight line motion. I mean the constant speed and a straight line as well. Okay, what is the reason behind that? Reason is that the relative acceleration between projectiles is 0, because see, acceleration of A is g and acceleration of B is also g. So acceleration of A with respect to B is acceleration of A slash B is acceleration of A minus acceleration of B, that's g minus z. So this happens to be 0 whenever as the relative acceleration is 0. That means relative acceleration is 0 implies the relative motion is of uniform velocity. So by subtracting accelerations, we can conclude that the relative motion has constant velocity. So it is easy to find out that. So to find out minimum distance between projectiles, so to find minimum distance between projectiles, so suppose this is the case. Now this projectile A is fired at this angle 45 degree at velocity of say 100 root 2 meter per second, and projectile B is fired at 37 degree with a velocity of, say that's also 100 meter per second, that is 100 meter per second, and the distance between the projectiles is, it happens to be 10 meter. It's kept very less because they won't drop actually, right? They won't drop on ground, right? So they'll fly apart in air. That is why this is kept less. So to find minimum distance between projectiles, so projectiles A and B are thrown with the initial velocities 100 root 2 meter per second and 100 meter per second, making the angles shown in the diagram. So here we have to find minimum distance between projectiles. Obviously they will not drop, and these all calculations are done while both are flying. So this velocity 100 root 2, we can have components. Say if you have x-axis here and y-axis here, so this component is 100, this component is also 100, while this was 37 degrees, so this was 100, so this component is how much? 100 into 4 by 5, 80, while that component is 100 into 3 by 5, that's 60. This is 60. Okay, so we have to observe from anyone. So for the initial velocities UA and UB, so it's like this: VA with respect to B is VA minus VB. Now VA is how much? UA plus GT, all with vectors, minus UB plus GT, because both are having accelerations. Now this G will cancel out, so if VA minus VB is always UA minus UB. So UA is how much? 100 I cap plus 100 J cap minus UB, that's minus 80 I cap plus 60 J cap. So that's 180 I cap plus 40 J cap. That's it. So this is VA with respect to B. Now, as we have found out VA with respect to B, now if you observe, so we are fixing our reference frame to B. So let's see the path of A with respect to B. So it's 180 this way, 180 this way, and 40 this way. So the resultant velocity is this way, this one. So this is VA with respect to B, same as UA with respect to B. So this is the path of A. This is path of A with respect to B. So there you have to find the minimum distance. So minimum distance between A and B, obviously it's the perpendicular distance. So from B you have to draw this perpendicular. So this, as this distance was equal to, this was how much? 10 meter, right? This was 10 meters. So this is D minimum. So minimum distance between A and B is this one, D minimum, equal to 10 sine theta, this much meter. So here sine theta, you know, from this vector triangle we can find sine theta. So that's 10 into this 40 by, see, anyway this dimensions will cancel, no? This is a vector triangle, So this 40 by this VA with respect to B, so that's 180 square plus 40 square. So this is the minimum distance between A and B. There are certain all slightly different types of problems also. Suppose this one. So will the projectiles collide or not? Collide or not? See, there are a series of diagrams. I will draw two of those. So that is 37 degree. This is 50 meter per second, and that's 45 degree, and this happens to be 30 root 2 meter per second, and these are two projectiles, and the distance happens to be, distance I will take less because I have to make sure that they won't fall on ground before they collide, so it's kept sufficiently smaller than the sum of the ranges. Okay, so here it is, the projectiles A and B are thrown from ground with velocities 50 meter per second and 30 root 2 meter per second as in figure. Okay, so will they collide or not? That's the question. Now there are various ways of solving the problems. I'll tell you the easiest one. The easiest method is that of relative motion. That means you be yourself B. That means fix your reference to B. So B is the reference. Observe from B. B is the reference. Observe A with respect to B. Okay. So you know that velocity of A with respect to B is obviously from the previous problem, you know, it is UA minus UB. VA minus VB is same as UA minus UB because their accelerations are same. So relative acceleration is 0. So UA, what's UA? If you choose this as x-axis and this vertically upwards as G, vertically upwards at y-axis, so this component is 40, so 40 I cap plus 30 j cap minus UB means this minus 30 I cap divided into components, this were 30 and these are the 30 plus 30 j cap. So what do you get after subtracting? 70 I can. So that means with respect to B, let me show in the next page. So B is kept at the reference. So with respect to B, A is having a velocity how much? 70. Okay, so that's the most important thing, is this is the direction of VA with respect to B. So as they will not fall, I mean the sum of their ranges is much bigger than the distance. So that's 10 meters. So from B, A will move directly towards B. So that is the only way they can collide, because in the path the velocity of A with respect to B always remains constant with time while they are flying. So the collision condition, the condition for A and B to collide is that A will directly crash onto B. That means the velocity vector of A with respect to B is directly towards B. That is the one and only way that a collision between A and B can happen. So our conclusion is that will they collide or not? Yes, they will collide, because VA with respect to B is directly towards B. If this would have happened, say if VA with respect to B were this way, then obviously no collision will happen. It's not possible, because anyway the relative velocity is going to be constant while they are flying, so this will miss A by this distance, minimum distance. So here this is the one and only way collision can happen. It tries to crash onto B directly. One more problem is like this. Say there are two such platforms. Yeah. This is thrown at a velocity that's 45 degree. Now this is thrown at a velocity 100 root 2 meter per second, and this is thrown at certain velocity, say u1 is equal to let me think, u1 is equal to say 100 I cap plus some vj cap, right? 100 I cap plus vj cap. So now these all distances are given, and this is thrown from a slightly high platform. This is the ground level, and this is a platform. Say that these all dimensions are given. Suppose this is given as a distance of say 20 meter, and this is given as a distance of say 30 meter. Okay, question is that the projectiles A and B are thrown. Projectiles A and B collide in midair. That's given, they will collide in midair, bang, somewhere while they are flying. So find V. So for the collision between A and B to happen in midair, find the value of B. So there is a much more difficult way which I would suggest you not to do, is this way. This will come via this path, this will come via this path, so bang, they will collide. So you can calculate the x displacement here, and the x displacement from here, and the y displacement from here, and y displacement from here. Equate the y displacement and summation of the x displacement, this and this has to be 30, and the y coordinates from this level, ground level, has to be same. But don't go for that method, go for the easier and the more convenient method of relative motion. So we can observe from say A or B. Suppose observe from A, or you can also observe from B if you like. Observe from A means now this A becomes the reference frame, so A will be at rest with respect to A. Now say you construct the axis x and y like this. So here u1, so you are looking with respect to A, so velocity of B with respect to A is ub minus ua. So ub is, I can can directly write velocity of B with respect to A. The point is that velocity of B with respect to A should be along this direction. For that to happen, see, because when once again I am saying that these are two projectiles, their relative acceleration is 0. So for the collision between A and B to happen, with respect to A, B should have a velocity directly towards A. There is no second option for collision to happen. So VB with respect to A is UB minus UA. So UB is how much? UB is minus 100 I cap plus 100 J cap minus UA is 100 I cap plus V J cap. Okay, so VB with respect to A is minus 200 I cap plus 100 minus V times J cap. So that's a vector VB with respect to A. So this component happens to be 200 this way, minus 200 means 200 this way, and this component happens to be 100 minus V, and what about this distance was 20, this distance was 20 meter, and this distance is 30 meter. So obviously this theta, so tan theta, if you look from the vector triangle, tan theta is how much? From the vector triangle, tan theta is 100 minus V by 200. From this real triangle, means from this point B to this point A, this is this platform and ground. From this, tan theta is 20 by 30. So let's solve V from here. So that becomes 200 minus V by 200 equal to 2 by 3, implies 100 minus V equal to 400 by 3, implies V equal to 100 minus 400 by 3, that's minus 100 by 3. So V should be minus 100 by 3. That means, as although it is shown, it is thrown upwards. For this collision to happen, it should be thrown this way. It should be thrown in a direction like this, so that this component, this horizontal component is 100, and this component is 100 by 3 downwards. Then only this collision will happen.